Okay, are there any questions?
I showed her the post.
No.
Just got around to it. He had it.
We'll continue talking about, we looked at some reactions and estimated delta H and delta S. Can we do that?
I don't think so.
No. All right, let's take a look at some reactions and then.
We were looking at 5B. That's where we left off.
Yep. We just established that it was an exothermic reaction and then the conflicting driving forces. Even though delta S was less than 0, delta H was
Talk about how delta H and delta S don't agree all the time.
conflicting driving forces. Yeah.
All right, so what do we do when we have a delta H and delta S that conflict? They don't necessarily cancel each other out. I mean, one could dominate over the other. And we have to figure out what might happen. And so we'll go on to C. If we look at C, we have sulfur trioxide plus hydrogen yields sulfur dioxide plus steam, H2O gas. If you look at delta H, what do you think for delta H? Endothermic or exothermic? Or no change?
Looking at C, right?
Mm-hmm. Can you guys see that?
Yeah.
SO3 plus H2. Endothermic? What makes you lean towards endothermic?
Breaking the bond from the SO3.
Actually,
Breaking bonds from SO3.
I want to change my mind. Because the oxygen bonds be a lot stronger.
Potentially, it could be stronger. One thing to think of is this. Although this could be tricky, what kind of reaction is it? It looks like a redox reaction. And so, if you think SO3 versus SO2, probably both are pretty toxic. Wouldn't you think? Both you wouldn't want to be breathing. And so that leaves the difference between H2 and H2O. Which one do you think is more stable, H2 or H2O? H2O by far. And so I would think this is exothermic because I would rather have a mixture of water and SO2 than a mixture of hydrogen gas and SO3. Don't you think?
You're ignoring the bonds that are breaking.
Well, the bonds are breaking, but
Right.
we are also forming bonds. And so, yeah, we're breaking the sulfur oxygen, one of them, and we're making a hydrogen oxygen bond. Hydrogen oxygen bonds are fairly strong as well because water is so stable. And so we break bonds, but we're forming the same number of bonds. And so the net change, it's hard to say, in terms of bond energies. If there's a significant difference. And so I would think in this particular case, you'd think in terms of mixture, hydrogen mixture in the mixture versus water in the mixture. Whenever you see water, you should think stable. Water is stable, unreactive. So that's what we have. And so I think exo, but as far as entropy goes, what do you think is more ordered? What do you think is more disordered? Yeah, I would think the entropy doesn't change much. And so this looks exothermic. If the entropy doesn't change much, then this should be a spontaneous reaction. Overall, it should have a driving force. D, we're going to skip that. And so sometimes we can kind of get an idea, but it's hard to because we don't know how to weigh entropy and enthalpy. In fact, the first thing we need to be able to do is how do we calculate delta S? You know, delta H we can. We can just use appendix D data, but what about delta S? What are the ways to determine delta S? Well, you know, delta S is easy to calculate. Delta S is just equal to S final minus S initial. Well, then there's a problem. You know, where did these values come from? Did I talk about absolute entropies? No. It's a Chem 1A kind of review. Where did these come from? So let's do a little bit, not much, of Chem 1A review here. Delta U equals U final minus U initial. You know, delta U is called the change in internal energy. U final and U initial are called absolute internal energies. Do we ever determine these? The same thing with delta H. Delta H is H final minus H initial. And so the question are absolute internal energies or absolute enthalpies ever used? Does anybody remember? So, you know, to calculate delta H, we just need H final and minus H initial. And you go, oh, that's easy because don't we have those in appendix D? You know, products minus reactants? We do, but the ones in appendix D are not H's, they're delta H's. And so the easiest way to determine delta H is to sum up the delta H's of formation of the products minus the delta H's of formation of the reactants. But here I'm talking about absolute enthalpy. Are absolute enthalpies determined? In other words, we have a reaction like this. Methane plus O2 gas is less stable or more stable than H2O liquid and CO2. Yeah. And so CO2 gas should be more stable than H2O liquid. This you just use experience to tell you. You know, if you filled up the room with methane and oxygen, that's an explosive mixture. Whereas is CO2 and water an explosive mixture? No, not even close. And so that tells me that methane and oxygen has a higher, we call internal energy, or higher enthalpy. These are absolute, than CO2 and water. So we're looking at U final, U initial, or H final, H initial. This is from Chem 1A kind of thing. So if it's not that familiar, go back and take a look at it. So then the delta U or the delta H is simple, right? You calculate it. H final minus H initial. Did I talk about internal energy already? No? Let me review a little bit about internal energy. Let's just use internal energy. Normally chemists use internal energy or enthalpy?
Enthalpy.
Normally chemists use enthalpy. Why do they use enthalpy? instead of internal energy? Oh yeah, constant pressure.
Yeah.
Enthalpies, we do most of our reactions under constant pressure conditions, so it's just more convenient. But let's talk about internal energy here for a minute. And so the internal energy of methane in 2O2 gas, I can balance this. So 1 mole of methane and 2 moles of O2 gas will have a higher internal energy than 1 mole of CO2 gas and 2 moles of liquid water. There's a change in internal energy when we combust the methane. But that change is going to result from U final minus U initial. That is the final internal energy minus the initial internal energy. And so what is the initial internal energy equal to, and what is the final internal energy equal to? How do we get the internal energies? Well, the internal energies are going to be equal to the total energy. What is the total energy? The total energy from physics, you've learned this, is equal to the kinetic energy, E sub k, plus the potential energy. So I'll call it this PE. Kinetic energies is related to motion and temperature. EK plus potential energy. When I combust my methane, it's going to combust at 298 Kelvin, let's say, at room temperature. And what is the temperature of the CO2 and water going to be? Normally the temperature skyrockets, it goes up. You know, you burn the flame, it goes like 800 degrees C or so. The temperature skyrockets. And so should this be about 800,000? Okay. If so, the kinetic energy skyrocketed. But normally what we do in thermodynamics is this. We start at 298 and we're going to end at, this is what we normally do in your calculations, all the Chem 1A calculations. We did an initial temperature of 298 and a final temperature of 298. And so the temperature didn't change, right? Well, the temperature does change, so how can I resolve this? In other words, if I combust the methane in here, is the CO2 in the water going to stay at 800 degrees C forever? What's going to happen? Eventually it's going to cool down back to room temperature. So this doesn't stay there. And so this cools down. Well, where did all that heat go? Into the surroundings. This heat went into the surroundings. But we don't care about the surroundings right now. We're just looking at what happened to the system. When we look at the system starts at 298, ends at 298, which tells me that the kinetic energy initial is the same as the kinetic energy final. This kinetic energy is just proportional to temperature. The temperature is the same kinetic energy. Right? And so nothing happened here. And so there was a change in potential energy. And this change in potential energy is that, in fact, we could calculate kinetic energy. That's not that difficult. Go back to chapter 6 and look. You remember that? That's kinetic energy for translations. And we add vibrations and rotations to that. We can determine the kinetic energies. And so the kinetic energy initial can calculate that. Kinetic energy final can calculate that, but we don't really need to because it didn't really change here. And so all we have to determine is the potential energy. And so this is from Chem 1A. Chem 1A is the potential energies are very difficult to determine. Why? The potential energies are very difficult to determine because what is it? Now, if you have methane and O2, you're looking at the bonds, any kind of intermolecular forces. You know, typically when we break things, it costs energy. And when we form them, releases energy. And so here, we got to break a lot of bonds. Not only that, there's energy stored in electrons as well, because if we want to remove electrons, it's going to cost us energy too. And so there's potential energy in the bonds, there's potential energy in intermolecular forces, there's potential energy in the electrons, potential energy in the nucleus. The potential energy in the nucleus, well, what's holding the protons and neutrons together? Nuclear forces. And so this is very difficult to determine, because where is the absolute zero of potential energy? Where does something have no potential energy? Absolutely no potential energy. Well, when everything's been completely destroyed, right? It can't. And so this is difficult, and therefore we don't determine these. We never calculate delta U based on that. Since enthalpies, I'm not going to spend too much time on this. But if we looked at an enthalpy diagram, enthalpy diagram is slightly more complex because H initial would be U initial plus PV initial, and then H final would be U final plus PV final. And so enthalpies just have this PV state here. There's a reason for that. But this is the same thing. PV is easy, but the U's, the absolute internal energies, would be difficult. And the U's, it's not the kinetic energy that's difficult, it's the potential energy that's difficult. But, and so absolute enthalpies run into the same problem. People do estimate them, but the errors associated with those estimates are too big to be of any use. And so delta H's and delta U's are determined differently, whereas delta S, there's no problem. Delta S, this is the main way we calculate delta S, from S final and S initial. And so how are these determined? These are determined S final. Different ways. S can be determined from the Boltzmann equation. The Boltzmann equation just says that S is equal to K ln of W. K is the Boltzmann constant, which is just R over Avogadro's number. So it's the gas constant per molecule or per whatever, per particle rather than per mole. W is the number of ways that the system can be arranged. Whatever you're looking at can be arranged. So, if there's only one way to arrange things, if there's only one way to arrange things, can it get very disordered? No. And so, if there's only one way to arrange things, what is the entropy? The absolute entropy. 0. The more ways, if there are a billion ways to arrange things, then you're going to see more disorder because you don't know which particular arrangement you see. And so as the number of ways increases, then the entropy increases as well. Well, if you have a mole of water, and in fact this is more than a mole. A mole of water is about 18 milliliters. And so if we have this much water, how many ways are there to arrange the water molecules in there? When I say ways to arrange it, I could move this hydrogen a millimeter up, or actually I can make a millimeter, that'd be huge. But I could move this hydrogen up a little bit, this hydrogen down a little bit. Each orientation is a way to arrange it. Now if you have an Avogadro's number of water molecules, and then there's free space, the molecules are touching, but there's still some free space in there, then how many different ways? It's enormous. If we're talking about one particle, no big deal. This is why physicists don't care so much about entropy, because usually physicists are just looking at one ball. You know, how many ways are there to arrange a ball in space? Well, it's spherical, not that many. And you can put them in positions. But if you have a mole of balls, then all of a sudden entropy is going to be quite significant. And so we can calculate it. And so if we know W, then can calculate. How do you figure out W? You have to do some statistics or whatever else to figure it out. And so this is it. This is where we're going to leave the Boltzmann equation. We're going to go to some other relationships.
Sorry, Professor. The constant, it's R over Avogadro's numbers.
Yeah, R over Avogadro's number.
What's
R? R is the gas constant, 8.314 joules. Kelvin divided by 6.022 times 10^23 per mole. So moles it counts on. It turns out that changes in entropy are related to heat. And so delta S can also be shown to be equal to Q reversible over T. Reversible just means reversible heat exchanges. We aren't going to get into it in much detail. All right, so from this, well, delta S is equal to S final minus S initial. This is equal to Q reversible over T. And so if we want the final entropy, that is, what is the entropy, then this would be just Q reversible over T plus S initial. Then we're going to have something called the third law of thermodynamics. The third law of thermodynamics basically says this. The entropy of a perfect crystal at 0 Kelvin is 0. So if you have a perfect crystal at 0 Kelvin, how many ways are there to arrange the particles that make up the crystal? If it's a perfect crystal, then each particle has a specific position that it must occupy. And so there's only one way of arranging the particles in a perfect crystal at 0 Kelvin. What happens if the temperature starts to go up? You know, if we go from 0 Kelvin to 10 Kelvin, what happens? Then the particles start to move. You know, there's vibration. As the particles start to move, then there are different ways to arrange it because there are different positions for that particular particle. And so the entropy will start to increase. And so here, you know, W is just going to equal 1, and S is equal to 0. Okay, so if we make this final entropy relative to initial entropy of a perfect crystal at 0, then this term should go to 0. If this term goes to 0, then the final entropy is just related to the heat at a given temperature. And so what we'll do is I'm going to skip some stuff. We're going to combine these two, this one, and then do some math. To get that the absolute entropy is related to, I'll just say proportional to this. me try to make it easier. At T. Okay, what this means is this is going to be the area or integral of the heat capacity versus T. And so what we do is this. You determine the heat capacity at different temperatures. And so if we look at water, we can measure the heat capacities doing calorimetry experiments. These heat capacity experiments can be done to very low temperature, almost zero. So we start to collect some data about the heat capacities here. Can't go all the way to zero. But with the third law, we know, at 0 Kelvin, what should the heat capacity be? Zero. You can't. Heat is kinetic energy. You can't move them. 0 Kelvin. And so everything is in its place. And so the heat capacity of ice is kind of low. The ice. But when you hit 273 Kelvin, the heat capacity is going to jump. Why is that? All of a sudden, the heat capacity jumps significantly. At 273 Kelvin because solid to liquid. And we have liquid water, and then eventually we're going to boil it. Is the heat capacity of steam greater or lower than liquid water? What has a higher heat capacity?
Water would have a higher heat.
Yeah, actually, interestingly enough, water has a higher heat capacity. Steam has a lower heat capacity. Actually, I should make it even lower. So we get something like this. It turns out the absolute entropy is the area under this curve from T to T final, T initial to T final. Here's T initial. Where's T final? Well, T final is anywhere on this curve, once we have the data like this. Why does, let me digress for just a second. Why does water have such a high heat capacity? Liquid water.
Hydrogen bonding.
Hydrogen bonding. So there are a lot of ways that water can absorb energy. One is to break the hydrogen bonds, another is to cause vibrations, another is to cause rotations. And so a lot of ways to do that. So if I wanted the absolute entropy at this temperature here, T, then I would just determine the area under this part of the curve, and that would tell me the entropy at T. I could get the entropy at T2, let's say, here. We'll call that T2. This would be entropy of 2. We just determine the area under that curve. As I increase the temperature, the area is going to climb. This would be the next temperature here. Eventually, out to here, I would have to determine the entire area under this curve, which is going to give me a fairly big entropy. Well, that's a lot of data. And so where do you think we would find most of our entropy data? What temperature do you think is most useful? If we were going to pick one temperature, what temperature would you find most useful to determine the entropy at? Of anything, of water. Room temperature. Room temperature is going to be the most useful. And so we want to determine the entropy at 298 Kelvin. The entropy at 298 Kelvin is going to be this. So that would be the entropy at 298 Kelvin. For the other temperatures, we just have to look it up in the other tables. Otherwise, this would be a lot of data just for water. Because we're interested in a lot of different chemicals. To determine those. Okay, so if you do this and then you measure the heat capacities at different temperatures for a whole bunch of different substances, and then you compile it actually into volumes of tables. And from all that data, we pick out the ones at 298 Kelvin to put into Appendix D. And so if you look at Appendix D is for 298.15 Kelvin, room temperature. And we'll list the absolute entropies. What does this little superscript mean here?
Is it the absolute?
No. Those are absolute. You see, this is an absolute. Is this absolute enthalpy? Oh, these are delta H's. This is absolute. Oh, these are the heat capacities. What does this little P mean? Constant pressure. So these are the heat capacities of constant pressure. So going back to the entropy, this little superscript means standard thermodynamic conditions. Standard thermodynamic conditions are what? Temperature of 298, is that standard?
Yeah, 25 degrees Celsius.
25 degrees Celsius is not standard. It turns out there's no standard temperature. And so you could find standard entropies at different temperatures. For example, this could be the standard entropy at 298, but we could also get the standard entropy at T3. Let's say the standard entropy at T3 would be this entire area. And so the standard does not refer to temperature. The standard refers to other constraints, like pressure. Standard pressure is 1 atmosphere or 1 bar. This one, it says 1 bar. And what else? What else is that the solutions are at 1 molar. And so those are the two constraints for standard thermodynamic conditions, pressure and concentration. Temperature is not. Now, when we got a table like this, what do you want to do with tables like this? We want to see how it's organized. So water would be probably under hydrogen or under oxygen. What do you think? Hydrogen. Here it is. It's water. So we get a table like this, we want to take a look at the entropy values. And so here's H2O liquid. H2O liquid has an entropy of 69.91 units. What were the units? Units are kind of odd. Units are joules per mole Kelvin. And so 69.91 joules per mole Kelvin. Is that a high entropy or is that a low entropy? Do you have a feeling for entropies? Probably not. And so to get a feeling, what do? You look for the lowest. You look for the lowest entropy and you look for the highest entropy. So let's look at the highest entropy on this page, 300.4. That looks like about it. There's high entropies elsewhere. And then let's look for the lowest entropy.
Negative 909.
So about 350.
Negative 99.6.
Higher.
Iron 3. Iron 3 at negative 315.9. And so we were seeing some entropies that are varying from minus 300 to plus 300 joules, just on this page. You want to look at the whole chart, but I don't want to scroll through this whole chart. It's too long. And so slow. Otherwise I would. All right. So 69 would be around in the middle, kind of, huh? Lower, higher? Middle? But there's something funny about this chart. Do you notice something funny about this chart? A minus 300 entropy means what compared to a perfect crystal at 0 Kelvin? It means iron 3 has a lower entropy than a perfect crystal at 0 Kelvin. True or false? This is 1 molar iron 3 plus AQ. The entropy of 1 molar iron 3 plus AQ at minus 315 is lower than a perfect crystal at 0 Kelvin, which has an entropy of 0. And so what's more ordered? Well, what's more ordered will have the lower entropy, and the lower entropy is iron 3. True or false? False. Iron 3 has a higher entropy. Is that right? So maybe I'm reading this backwards. So iron 3 has a higher entropy. That means iron 2 has a lower entropy?
Yes.
No, iron 2 has a higher entropy.
Iron 2 has a higher entropy? Well, one of those is true, the other is false. So which one is it?
You have 50%. Should go with false.
Iron 3 has a lower entropy than a perfect crystal at 0 Kelvin. In other words, iron 3 has a lower entropy than 0 is false. And that has to do with the quirks of using Appendix D. Do you guys remember hydrogen? Let's look at the delta H's of formation here. The delta H of formation of hydrogen gas is 0. Does that make sense?
Yeah.
Yeah, it makes sense because we're forming hydrogen gas from hydrogen gas. So we're going from H2 gas to H2 gas. What do you expect the energy to do? Nothing, because it's the same thing. There's no energy change. But what about H plus? We're forming 1 mole of H plus, 1 molar AQ, from 1 mole of, or actually not 1 mole, 1/2 mole of H2 gas. Is that a 0 energy process? In other words, to convert hydrogen gas to H plus AQ, does that cost 0 energy? But it says 0 here. And so is that right or wrong? It's right. So the way I explain this in Chem 1A is this. Imagine you have a temperature table in which they didn't write the units. Like here, there's a temperature of 315 and a temperature of 65, and somebody asks you, which one is a higher temperature? Automatically you'd say 315 is a higher temperature. But there's a problem. And the problem is this. This is in Kelvin, and this one is in Celsius. Now which one's a higher temperature? 65 is higher, right? And so without the units here, and by the way, units are very important. Units are very important because I noticed a lot of people probably would have gotten the buffer one right if they used units. You know? And so don't start ignoring units. That's a typical Chem 4 mistake. You don't want to. I'll tell you, nobody in a research lab would skip the units. Or definitely in grad school, they wouldn't skip the units. But here, and we shouldn't skip the units too. It's very important. Otherwise, we can't compare these two without units, right? So people had things canceling out that shouldn't have canceled out. But this table is like having the temperature table with two different units. So when I'm asking you to compare, I was asking you to compare Kelvin with Celsius and Celsius with Kelvin. You can't compare the two. Right? And so if I was asking you which one has a lower entropy, you can't compare the numbers. Because iron 3 is on a different scale than a perfect crystal. Why do we have two different scales? Actually, three different scales. You know, Appendix D has three different units in here. Appendix D is like having Kelvin, Fahrenheit, and Celsius. Just showing the numbers because everybody expects you to be able to figure it out. But, you know, I realize that every time I ask somebody about this, they don't have a clue. So probably it's the best thing to do is put some kind of marker on here so that people don't run into that problem where they're comparing these two numbers directly. And so this first came up with delta H. The first time this came up was with this. Is this the Kelvin or is this the Celsius? 0. This is the Kelvin, 0. Is this the Kelvin? No, this can't be. Or maybe it is. Could both of these be 0 simultaneously? No. Well, they could if we put units on there. You know? If we put units, I put 0 Kelvin here, and here I put 0 degrees C. And let me do one more. Here, what would I put? Kelvin, Celsius, or Fahrenheit? I put Fahrenheit here because I know this table. I know how you're supposed to use this table, but this table turns out to be a trap for the unsuspecting student who doesn't know how to use Appendix D, right? Which is why I spent so much time talking about this in Chem 1A. Okay, why? What happened here? What happened here is this. You know, if you've noticed, you'll see a pattern. You know, after we assign the biggest and the smallest, then you start to look for patterns. One of the patterns you'll notice is that, you know, the compounds, this is after some time, the compounds are on the Kelvin scale. The cations would be like on the Celsius scale. And the anions would be like on the Fahrenheit. And so we never compare cations with compounds or cations versus anions, because the cations are on a scale by themselves, the anions are on a scale by themselves, and so compare other cations to other cations is no problem. Anyway, having a negative entropy would be a violation of what law?
First law of thermodynamics.
Well, not the first. The third law. The third law of thermodynamics would be we can't have a negative entropy. How can you have something that's more ordered than a perfect crystal at 0 Kelvin? It's impossible. That's like saying I have minus 315 Kelvin. It's impossible. And so this is not Kelvin. This is not the absolute. And so why do we have this? Well, if you wanted to go for a discussion of why we have this, go back to chapter 7. and look at the delta H of formation of HCl. This is just a quick review here. Delta H of formation of HCl, we're forming H plus aqueous and Cl minus aqueous. If we do some calorimetry measurements, we see per mole of HCl, we release 167.2 kilojoules worth of heat in forming that from the elements, hydrogen and chlorine. Now, how much of this heat belongs to the formation of H plus, and how much of the heat belongs to the formation of chloride? You know, is H plus half of it and chloride the other half of the heat? Or is it like an 80-20 split or 90-10 split? What is the split here? Is that something that's easy to determine? No. Since it's not so easy to determine, do you know what people do? They assign an arbitrary 0. An arbitrary 0 would be like, I mean, if Fahrenheit was thinking, okay, what's the absolute coldest temperature? Is that something easy to do? No. So Fahrenheit came up with an arbitrary 0. Celsius's 0 isn't so arbitrary, but in a way, it is arbitrary because Celsius's 0 is the freezing point of water, right? Melting point of ice. And so what's our arbitrary 0 from delta H of formation? Our arbitrary 0 is that when we form HCl, all the energy is associated with the formation of chloride. And none of that energy is associated with the formation of H plus. Well, that's a serious error, isn't it? But we can see that. Let's flip back because it's minus 167.2. The formation of H plus is 0. That means the formation of chloride must be all of it. And so when we look at the formation of chloride, it's all of it, minus 167.2. And so that's a serious error because some of that energy must be associated with the formation of H plus, right? How much? We don't know, but this serious error is okay because one is too high, the other is too low, and when you add them together, the two errors cancel each other out. And so can you ever form a cation without an anion? No, electrical neutrality dictates we've got to form a cation and an anion. We can't just give you a bottle of cations. The systematic error cancels out, so we can't compare relative to absolutes. This is absolute. This is absolute. This is relative. No, this would be absolute too. So does that make sense? It's a brief. And so the same thing happens with S, entropies. When we look at the entropy of, let's go forward one page. When we look at the entropy of H plus, if you have a 1 molar H plus solution, at 298 Kelvin, does that have 0 entropy? Is a 1 molar H plus solution at 298 Kelvin perfectly ordered? No, not even close, right? And so this is what we call an arbitrary 0. Though, where's all the entropy? Well, we can't form a cation without a anion. So let's take a look at HCl. What's the entropy for the formation of HCl? Let's say 186.9. H plus, 0. These are absolute entropies, so when I say for the formation, I'm making the reaction there. Cl minus, oops, did I read the wrong column? 56.5. I read the wrong column. Look at that. For HCl, AQ, 56.5. I was reading HCl gas. So do you see that? So the entropy of HCl is actually 56.5. How much of that 56.5 is due to the disorder in the H plus, and how much of it is due to the disorder in the Cl minus? We're saying all of it is due to the disorder in the Cl minus, and the H plus is perfectly ordered. Does that make sense? No, it doesn't, but we can't separate it, so that's the easiest thing to do, and therefore it leads to an error, but that error cancels out when you add the cation and the anion to get the compound. Okay, the problem is that people want to compare certain things that people don't know. So when I ask the question, now let me re-ask this question. What has a lower entropy? A perfect crystal at 0 Kelvin with an entropy of 0, or iron 3 plus with an entropy of minus 315.9. What has a lower entropy? Tell me.
The crystal.
The perfect crystal. What has a lower entropy? Iron 2 plus minus 137, or iron 3 plus minus 315. What has a lower entropy?
3 plus.
Iron 3 plus with an entropy of minus 315. What has a lower entropy? Iron 2 plus at minus 137, or iodide at 111.3.
Which has a lower?
Lower entropy.
Will it be 2
You
plus?
You can't compare the two, right? You can't compare the two reliably. Okay? All right, so this is Appendix D. We're going to be using Appendix D quite a lot. And so the calculation is very simple. Anybody can do the calculation, right? S is just S final minus S initial, delta S. And so let's do the calculation. But knowing how to use this table, does anybody, I mean, is using this table easy? No, it's a pain because, you know.
So when we actually use Appendix C, are we going to add like corrections to it?
We don't add any corrections.
Okay,
We just use it as is.
All right.
All right, so let's look at a calculation here using Appendix D data. Number 77, oxides of nitrogen are produced in high temperature combustion processes. The essential reaction is N2 plus O2 gives 2 NOs. All right, the first thing is, let's do this qualitatively. Delta H, greater than 0, about equal to 0, or less than 0? What do you think? You know what this looks like? This looks like a combustion reaction, right? We're combusting nitrogen with oxygen to form an oxide of nitrogen, NO. And so typically combustion reactions are exothermic or endothermic? Exothermic. And so normally you would say exothermic in a combustion reaction. But you also know something about nitrogen and oxygen. This room is filled with nitrogen and oxygen. Are we breathing in NO too? NO is toxic. No. So you would know that nitrogen and oxygen form a stable mixture. In fact, nitrogen is very unreactive. Nitrogen is called a pseudo-inert gas. One of the reasons it's called a pseudo-inert gas is because it's got a triple bond. It costs about 1,000 kilojoules per mole to break. And so it depends on which side you think is more stable. Would you rather be in a room filled with nitrogen and oxygen, or a room filled with NO?
Nitrogen and oxygen.
Probably nitrogen and oxygen. NO is a lot more reactive, right? Although oxygen is highly reactive. But maybe that's not the best way to compare it, but maybe we'll do that. And so what would you guess for delta H? Exo or endo?
Endothermic.
Probably endothermic. Maybe exo. I don't know. See a question mark here. What about delta S?
Same.
Delta S, maybe about 0. Not much change. All right, now we don't want to go qualitative anymore. Let's go quantitative so we can put some numbers on this. And we don't have to guess what's going to happen. And so let's first get delta H. What's the easiest way to calculate delta H?
Appendix D.
Appendix D and delta H is formation. And so let's go to Appendix D, take a look at the delta H of formation. So NO gas, delta H of formation is 90.25 kilojoules per mole. Energy is extensive. What does extensive mean? Extensive means it depends on the amount. And so if you burn 1 mole of methane versus 2 moles, you're going to get a different energy. You know, if you burn 2 moles of methane, you'll get twice as much energy. And so delta H, we care about how many moles. So we got 2 moles of NO. Each mole is 90.25 kilojoules to form. And so delta H for this minus the reactants. The reactants here are nitrogen. What's the delta H of formation of nitrogen? What's the delta H of formation of oxygen? 0. Both of these are 0. This is forming the elements from the element involve no energy. So this is 0 plus 0. So products minus reactants is going to give me 180.5 kilojoules. And so this says driving force or no driving force? No driving force. So this means it should be non-spontaneous. Spontaneous. Now let's go to delta S. Okay, these are under standard conditions because they're under standard conditions and at 298 Kelvin. We have to put 298 Kelvin here because there's no standard temperature. So when we go, we have to look at the entropy of NO, 210. When I look at a whole bunch of these entropies, you'll notice another pattern. Solids have fairly low entropies, between about 0 and 100. Liquids, the entropies are about 100 to 200. Gases have entropies typically over 200. So here we have NO gas, it's 210.8. N2O gas, 219.9. And so when we compare NO and N2O, let's just do this quickly here. They're both gases, and so they're both going to have high entropy. Now N2O has 3 atoms, NO is diatomic. With 3 atoms, you're going to have more ways it can vibrate, which increases entropy. And so with a 3-atom molecule, you see the entropy bumped up a little bit, 9. Not much. And so primarily it's because of the gas. So we have some of these are a little weird, like this solid has a very low entropy, or actually this solid has a fairly high entropy, ammonium chloride. Well, let's continue on here. NO 210.8, we have 2 moles of that. So it's the same thing. I mean, the more moles, 1 mole is about 25 liters, 2 moles about 50 liters. If you have 50 liters of NO gas, there are a lot of ways to arrange the atoms or molecules in that. And so 2 moles times 210.8, the units here would be joules per mole Kelvin, or Kelvin mole. So moles cancel, gives us joules. minus the entropy of the reactants. Okay, what's the entropy of nitrogen? Is the entropy of nitrogen 0? No. The entropy of nitrogen is not 0. It's 191.6. We'll simplify that. So we have 1 mole of that, so it's going to be 191.6 joules per Kelvin plus the entropy of oxygen. The entropy of oxygen, 205.1. You see, a lot of different species in here. Like, for example, ozone. Ozone, should it have a higher entropy or lower entropy than oxygen? Higher. It's 3 atoms. A lot higher or just a little bit higher? Just a little bit, because they're both gases, and one has 3 atoms, the other has 2 atoms. What about atomic oxygen? Atomic oxygen, should that have a lower entropy or a higher entropy? Lower, just a little bit lower, right? And that's what we see here. Just a little bit lower. And so, can somebody calculate the entropy? .9 joules per Kelvin. Now, the entropy says that this should be spontaneous. And so one says non-spontaneous, the other says spontaneous. Spontaneous just means it's driving force. So which one wins? Well, you know how I know which one wins? At 298 Kelvin, are we breathing in much NO? Which is a good thing. And so enthalpy wins here. This is dominant. But do we have to rely on observations to tell us that? I mean, how can we compare these two? How do we compare?
Can we go by the bigger number?
Well, they have different units. This one's in kilojoules, this one's in joules, so this is a bigger number. Maybe we could go by the bigger number. But this is in joules per Kelvin, so we got to get rid of the Kelvin in order to compare these two and convert it into kilojoules. So how can we get rid of the Kelvin? We can multiply by 298 Kelvin, the temperature, and then convert joules to kilojoules, and then we can compare the two numbers, see which one's the bigger number. Which one can dominate. And that's kind of what we're going to be doing. We just compare it, but we want some kind of theoretical basis for that. And so let's talk more about this.
Is there like a threshold for when it's spontaneous and it's non-spontaneous?
Yeah.
Should we know that threshold?
The threshold would be this. If this term dominates over this term, in other words, if this term is bigger than this, then it should be spontaneous. But that threshold is what we're going to talk about next. How do we compare this? The way we're going to compare this is by using the second law of thermodynamics. The second law of thermodynamics seems disconnected from what we've just been discussing, because the second law of thermodynamics in one sense says that all spontaneous reactions have a common feature. And so what common feature do all spontaneous reactions have? It's not that, delta H is negative. It's not that delta S is always positive.
Isn't it like the low activation energy or something like that?
Even with low activation energy, some reactions are not spontaneous.
Okay.
Well, I guess it's what you call low activation energy. And so what do all spontaneous, so this required a lot of observations and looking for patterns. The pattern nature that was observed for all spontaneous reactions was this, that all spontaneous reactions met this criteria, that the entropy of the universe increased, went up. And so if you want to know what's going to be spontaneous, all you have to do is determine the entropy change in the universe. If the entropy change in the universe goes up, then the reaction should be spontaneous. Well, how's that connected to this? This energy and enthalpy thing and entropy. We'll see in a minute. Because delta S of the universe, well, what's that? Delta S of the universe is equal to delta S of the system plus delta S of the surroundings. The system and surroundings together make up the universe. And so if delta S of the system is greater than 0 and delta S of the surroundings is greater than 0, or at least one, of those dominates and that's favorable, then this should go. Delta S of the system, this is easy because this we get from Appendix D. Appendix D, in fact, this is what we call delta S of the system because this is the reaction that we're looking at. And so in this case, the system looks good. So why didn't this reaction occur? It wasn't because of the system. It must have been because of the surrounding. And so it's got to be related to the surroundings. Entropy must have gone down. So let's take a look at that. This one is hard, because do you have an Appendix D for everything in the universe? No. So this would be impossible to calculate. So let's look at the delta S of the surroundings term in more detail. We can relate this to other things. In thermodynamics, this is often difficult to do, relating one thermodynamic variable to another. But delta S of the surroundings is also related to Q reversible over T. So this related heat exchange. What is heat exchange? Q. Q is just usually it's a transfer of kinetic energy from a hot object to a cold object. Hot objects have high kinetic energy, lots of motion. Cold objects have lower kinetic energy. So there's just a transfer of kinetic energy. Okay, then we know some stuff here because this would be Q reversible of the surroundings. We know from the first law of thermodynamics, and we've got to keep the sign convention correct, but the first law of thermodynamics says that energy is conserved. Energy is neither created nor destroyed. And so if the surroundings gains or loses energy, that must have come from somewhere. Where did it come from? The system. And so what we can do is we can relate the heat exchange with the surroundings back to the system. In other words, Q of the surroundings is equal to minus Q of the system. And so this is just the opposite sign. It doesn't mean this is exothermic, that's endothermic. This could be exothermic and then exo times negative gives us endo. And so this would be negative Q reversible of the system. And so now this is much easier to deal with because we have it in terms of the system. But Q is unreliable because Q is what we call a path-dependent function. Q is not a state function. And so what's the difference between a path-dependent function and a state function?
State functions are final and initial.
Yeah, state function just depends on the final and initial. And it's always the same. So for example, state function would be the distance, between point A and point B. That's always the same, let's say, distance, let's say the direct distance here. State function. But what would be a path-dependent function would be like the time. What's the drive time between point A and point B? The drive time could be highly variable, right? Depends on how many red lights you hit. In Torrance, there'd be a lot of red lights. It's like, so the drive time, it's not, and so Q is like that. Q changes. It depends on how you do the reaction. Q's not so reliable because if you're trying to base everything off the drive time, is the drive time always going to be the same? No, the heat's not always the same. Why? Because it depends on the path, right? There's a path-dependent function. How much heat? And so how do we make heat into a state function? How is heat made into a state function? Have you ever heard of that? Have you ever heard of somebody saying that heat is, we're going to make it a state function. We're going to make it so you always get the same amount of heat every time. And that would be like, okay, we're going to make the time the same. Each time I do this, it's going to take the exact same number of minutes. How do I do that?
Control the variables.
Control the variables, right. What you do is you place restrictions. And so it's not just free, any old heat. We have to place a lot of restrictions on heat, right? And so if you want the time to be the same, then you're going to have to control the path to make sure it's the same path each time. What else? And you have to make other restrictions. And so does somebody know the definition of H, of enthalpy? Can somebody tell me what the enthalpy is defined as? A lot of people will say, I asked for the definition of delta H. You know what people tell me? Oh, the definition of delta H is the heat of reaction. But that's not really the definition I wanted. Heat of reaction just doesn't do it for me. I need a more specific definition. So do you have a more specific definition of delta H or H? I don't like heat of reaction because is that path heat? State heat? What is that? Heat of reaction. A lot of people, delta H calculation, there's a difference. Anybody can do a delta H calculation. It's so simple. Sum up the delta H's formation of the products minus the reactants. But does that make you a scientist? No, because you can be a non-scientist and do that, right? It's just simple algebra. And so what would make you a scientist? What would make you a scientist is you know what delta H means. You know how it's defined, right?
Isn't it just energy absorbed generally and on?
Yeah, that's one way of saying it. It could be the energy. That's better.
I asked Google. Google told me enthalpy change is the name given to the amount of heat evolved or absorbed in a reaction carried out at a constant pressure. It's given the symbol delta H.
Okay, that's not the complete definition. Close. That's getting better. That's getting better. It's getting better, but this is important because even in science, a lot of stuff is being outsourced. You know, anybody can do these calculations, but not anybody can interpret what they mean. And so,
Isn't enthalpy just the internal energy and the constant pressure?
It can't be both constant pressure and constant volume. It can be either or. Either constant pressure or constant volume, but not both at the same time. Some reactions can be both, you know, but other reactions, if you try to do constant pressure and there's a lot of gas generated, it's not going to work. Well, anyway, the whole business for going through this is because we need the definition of delta H for the next step. The definition of delta H is we're going to make heat a state function. We make a heat a state function by one, doing constant pressure. Delta H and enthalpies are always constant pressure versus constant volume. If we're using constant volume, we better not be using delta H. We better be using delta U. Otherwise, we'd be getting the wrong answer. And so, you know, lots of people can do a delta H, but if they're doing a delta H calculation under constant volume conditions, they're going to get the wrong answer. They're going to write down the wrong answer. They might get lucky. They might have a reaction that it doesn't matter, because sometimes delta H and delta U are the exact same thing. Tell me when that happens. When is delta H and delta U the same? Like, if I ask this on a test, on Chem 1A, that's Chem 1A stuff. I'm not going to ask you on Chem 1B. But when is delta H and delta U the same? See, that's important to know, because otherwise you're calculating something that you have no idea if it's right or wrong. You're just guessing. And it's okay, because, you know, in Chem 1A, they might say, okay, we're going to make sure that it's always right, you know. But not necessarily, because once you go beyond Chem 1A and Chem 1B, then they don't care. You know, if you mess it up and you calculate delta H when delta H is not valid, then you're wrong. You just lost a lot of points, you know, in the next class. That's it.
Is it when there's no change in volume?
No, delta H is always change in volume. We use, you know, Jameson, delta H is the Avogadro's law version versus the Dalton's law. Have you heard Avogadro's law versus Dalton's law? Dalton's law is you sum up the partial pressures, you get the total pressure. Avogadro's law is you sum up the partial volumes to get the total volume. Can Avogadro's law and Dalton's law be simultaneously valid? No, it's an either-or situation. Either Dalton's law is valid or Avogadro's law is valid, but not both at the same time. Well, this is the same thing as delta H and delta U. Because delta H is constant pressure, which is Avogadro's law, and delta U is constant volume, which is Dalton's law. Constant volume, the pressures have to add up. Right? Because there's no room for the gas to expand or contract. Constant pressure, the volumes have to add up, otherwise the pressure is going to build up or shrink down. And so all this stuff is connected, but you can review it. This is not so critical here. It's just you should have an idea that this comes from the definition of delta H. So we do this under constant pressure. Delta H, that definition on Google would work if they just added one more thing. The one more thing they have to add is that we got to restrict the work. The only type of work we can have in delta H is what kind of work? The only type of work we can have in delta H is if we restrict it to minus P delta V work. Only. And so we place these restrictions, and then what we can do is we can convert Q into delta H. And so this becomes delta H of the system over T. And so what we do is we take something that there's no way to determine. I mean, delta S of the surroundings, right? And then convert that into something we can determine. Delta H of the system, easy. Appendix D. And so by some thermodynamic relationships here. Are we out of time?
4 minutes.
4 minutes, okay. And
One
so
more thing.
what we're going to do is we're going to substitute this back in here. And when we substitute it back in, we got delta S of the universe, which is equal to delta S of the system plus delta S of the surroundings. This has to be greater than 0. We want the total entropy of the system and surroundings to increase. So one can go down, but the other better go up in order to make it spontaneous. Well, delta S of the system, we know what that is, appendix D. But delta S of the surroundings is just equal to minus delta H of the system over T. And so now we have this in terms of the system. And so we're going to multiply by negative T on both sides. So we get minus T delta S of the universe. Actually, let's go ahead and do this. Let's just multiply by T. So we get T delta S of the universe is equal to T delta S of the system minus delta H of the system. And now let's multiply by negative. When we multiply by negative, we have to flip the sign. That is, delta S of the universe is equal to, actually let's change this. This is going to be delta H of the system minus T delta S of the system. Now this should be less than 0 rather than greater than 0, since we multiplied by the negative. And so we end up with this. T is a state function, delta S is a state function, so we have a new state function. This new state function we're going to define as delta G for the Gibbs free energy. And so delta G of the system is equal to delta H of the system minus T delta S of the system. And so if this is less than 0, then it's spontaneous. If it's equal to 0, it's at equilibrium. If it's greater than 0, it's non-spontaneous and wants to reverse. And so this is the second law of thermodynamics rewritten in a way that we can determine. Because delta H of the system and delta S of the system can be determined. And so how does this, how did we do this, delta H of the system? How did that come in? Well, that came in from what we call entropy. There are different forms of energy. For example, electricity versus heat. Which one is a more usable form of energy, electricity or heat? Electricity, because you can convert electricity easily into work or heat or whatever else, right? And so when we think about chemistry, there are different forms of energy in chemistry. We have,
Inert.
well, let's look at the total energy. The total energy is kinetic energy plus potential energy. Here. So this would go to CO2 gas plus 2H2O liquid. When we do a reaction, we start off at 298 and we end at 298 Kelvin. So where did all that heat go? Into the surroundings. And so we're going to have some kind of delta U that's going to emit energy to the surroundings. Well, what was that energy? Well, we look at the kinetic energy. Did the kinetic energy change? Here. Well, we started at 298, we end at 298. The kinetic energy is the same. So this is initial, this is final. And so the kinetic energy, delta EK is 0. And so it turns out that this is just a change in potential energy. And so we're going from what's called chemical potential energy to, this is going to release the energy as heat to the surroundings. And so what do you think has, what do you think is more ordered? Chemical potential energy or heat dumped into the surroundings?
Disorder?
Or either disordered or ordered. The heat has a higher entropy than chemical potential energy. Chemical potential energy is much better ordered. We can convert chemical potential energy into, for example, if you burn this, you can convert this energy into work. Is it easy to convert heat into work?
No.
No, but chemical potential energy, in theory, can be converted entirely into work as long as you minimize heat loss and heat generation. And so I'm going to stop here since we're out of time, but we'll talk more about energy entropy next time.
So when you say